No, es el Google.
I never saw it.
Here we go.
Twitter, dude.
Today we're going to talk about derivative of inverse functions. But before we go into the actual derivative of an inverse function, we're going to talk about inverses and a little bit of review of inverses and everything we should remember or recall from pre-cal and calculus regarding inverses. And see how much you guys remember about them. Okay? So, I don't know if you remember what inverses do to each other. So if I have a function and its inverse, what should they do to each other? They should cancel each other out, right? And we should always be left with this particular answer, and that answer has a special name. It starts with an I, and sometimes people have it stolen. An identity, very good, okay? So when two functions cancel each other out, okay, you will always be left with something known as an identity. And there are different identities depending on what you're doing. So for example, what would be the inverse of 5 through addition? What would cancel 5 out through addition? Negative 5, the opposite, right? So 5 plus negative 5 gives me 0, right? Okay, does that happen all the time when I have something and I add its inverse to it? I add its inverse. Yes, I should always get 0 because they're going to cancel each other out, right? So therefore 0 is the identity through what? Addition. Do you understand? Okay, what does 0 do to anything when I add it? 5 plus 0. Nothing. Okay, cool. Alright, what would cancel out 5 through multiplication?
0.
1/5, right? So 5 times 1/5 cancels out and I'm left with 1. Okay, how about 1/10? What would cancel out 1/10 through multiplication? Times 10, right? And what would we be left with? 1, okay? So therefore 1 is the identity through multiplication. What happens when I multiply by 1? Nothing, right? If I were to multiply by 0, because somebody said 0 is the identity, what would happen? I get 0, so something would happen, right? Okay? So the identity is something that does nothing to the problem when you're doing the operation that it's correlated to. You understand? Like 0 did not do anything when I added, 1 didn't do anything when I multiplied. Cool? Alright, when we're working with functions, we're actually working with the composition of functions. That's kind of like the operation that we're doing. We're composing one function. So we get the inverse and we plug it into the original function, or vice versa, we get the original function and plug it into the inverse, and they should cancel each other out and we should be left with something known as the identity. Okay, anybody remember what that was? For pre-cal and algebra 2.
Wait, what was?
Like when you were trying to see if two functions were inverses. Do you remember doing that? Where you had to get one and plug it into the other and show me step by step that everything canceled out and what should I have been left with at the end? Which is the identity through compositions of functions. X, very good. Okay, that x is my inverse. What happens if I plug in x into this equation? Nothing, right? Okay, didn't we just say that that's what the inverse is supposed to do? Yeah, okay. So when I plug in x in here, it does nothing to the problem. Do you understand? So that one was like this. If I had f of f inverse, right, if I got the inverse and put it into the original function, we should end up with the identity x. Everything should cancel each other out. Same thing for the other way around. If I got the original function and I plugged it into the inverse, we should also get x. We should get the same value. Got it? Yes? Alright. Anybody remember the steps that you had to do to find the inverse of a function algebraically? What was the first step that you had to do to find the inverse? Very good. Switch x and y, right? Okay, so that process of switching the x and y, once you do that, that expression that you have, or that equation, is already known as the inverse of the original function, right? We just, in math, we don't like them to leave them x equals, we like to make them y equals, right? So then after we did that, we had to make it y equals and then just label it as the inverse. You remember doing problems like that?
Yeah.
Yes? Okay, the main thing I want you to get from there is the idea that in order to find the inverse, I need to do what? I need to swap the x and the y value. Okay? What does the x values represent for my function? Starts with a D. The domain. And what do the y values represent?
The range.
the range. So if I'm swapping the x and the y's, I'm swapping the domain and the range, okay? And that's exactly what it means here. So it says, given an original function f, the inverse is numerically defined to be a function whose domain, okay, so the domain of the inverse is the what? Is the range of what? Of the original function f of x. Okay, we're talking about the inverse. So the domain on the inverse is actually the range of the original function. And whose range is the what? Domain of f of x. Basically what we just said. And in order to find the inverse of a function, we have to just what? Swap the x's and the y's. Okay? So we need to be able to understand the inverse a couple of different ways. One of them is graphically, and the other one is analytically or algebraically. So we're going to look at both aspects of it and how to work with them. Ready? Alright, so we're going to draw a graph here. And then I'm going to ask you to draw its inverse. So go 5 to the right, 5 to the left, 5 down, and 5 up. Ready? So let's graph the original function. I want you to put a point at negative 1, 1. And I want you to put another point at negative 4 and 2. And the last point, I want you to put it at negative 5 and positive 5. It should look like this. Let's label this one. This one was negative 4, comma 2. We're going to call this f of x. If I wanted to draw the inverse of f of x, how could I draw it? What do you think I could do to get the graph of its inverse? Switch the x and the y for what? So swap the x and the y values of all the points, and then connect the dots? Okay, so let's do that. So for f inverse, we're going to swap x and y. Here we go. So swap the x and y of this first point. So that would be negative 1, positive 1. Now it's going to be what? Positive 1, negative 1. Okay? This one was negative 4, 2. Now it's going to be 2 and 1, 2, 3, 4. Okay? And the last one was negative 5, positive 5. So now it's going to be positive 5 and negative 5. So this one's now 2, negative 4. And this function is the inverse of the original one, right? Cool? Alright. So what does it seem to be a reflection over? The origin
Of the line y equals x.
or the line y equals x? Which one? They're different. The line? So like if I drew the line right here, y equals x, and I flip this over, would I get this graph over here? Yes. Okay, so it is a reflection about the line y equals. Okay. Do you guys know what a reflection about the origin is? No? Okay. When we say something is symmetric with respect to the origin, that means that when I reflect it over the x and over the y-axis, I get the original picture back. Yes? So, reflection with respect to the origin would be a reflection about the x and about the y. Do you understand? So I would have to flip this what? over the x, over the y, and over the x. Will we get this picture?
Yeah.
No.
No, you wouldn't, because it'd be facing weird again. It'd be facing this way.
It'd be facing that way?
Yeah, because it'd be like, it'd be the upside down, yeah.
Very good. Okay, so do you see the difference?
Mm.
Right. What happens if I reflect with respect to the origin? Do the x and the y swap? Let's start off by reflecting over the y. What changes when I reflect this point over the y? It went from being at -4 to being at what? +4. So the sign of the x changed, right? When I flipped over the y. What happens when I flip over the x? The sign of the other letter, the y, changes, okay? So the only thing that happens when I reflect with respect to the origin is the signs of the values change. They don't switch position. You understand? Okay, so this is not with respect to the origin. Make sure you remember that. Good? Alright, so whenever you reflect over the line y equals x, what's going to happen is the x value and the y value are going to swap. Okay, and that graph will be the inverse of the original graph we had. Got it? So can you remember that? F inverse of x is formed by reflecting f of x over the line y equals x. Good? Okay. Over here on this side, we're going to talk about the analytical representation of the inverse and kind of what we already said. We said that if I had a function, so if f inverse of x is the inverse of some function f, then the following two things have to be true. F of f inverse should equal x, and f inverse of f should also equal x. Okay, both of those have to be true. You can't just check one of them and say, oh, okay, yeah, it's good. I plugged the inverse in there and I got x, I'm done. No, because when you swap it and you put the other one into the other one, you might not get x. You might get negative x, right? So then it fails the test. Okay, it didn't pass both of them. Has to pass both of them, and both of them have to give you x. Now maybe in your pre-cal classes, your teachers were nice and told you, no, you know what, don't worry. You're just verifying, it's going to work out. Just do one of them for the idea of practicing. They didn't make you do both of the checks all the time. Okay, but theoretically you are supposed to do both. Good? Now, sometimes, I don't know if you remember in Algebra 2 when you were working with matrices and they asked you to find the inverse of a matrix. Or maybe here when you were finding inverses of functions, you discovered that not all functions have an inverse. Did anybody remember how to test if something had an inverse before you started to look for it? Because that way, if it didn't have one, you didn't even bother checking for it. You just said no inverse. Anybody remember? Anybody remember how to know if something was a function? How do I test for something to be a function?
The horizontal line.
For a function? What is it for a function? The vertical line test, right? Do you remember doing that in Algebra 1? Yeah? For something to be a function, it has to pass the vertical line test, meaning that if you draw a vertical line, it can only intersect what? One. Okay? Now, for something to have an inverse, it also has to pass the horizontal line test, meaning that when I draw a horizontal line, it can only cross once. Okay? And if a function passes both of those tests, it's said to be a one-to-one function, meaning every x only has one y, and every y only has one x. It's like the perfect relationship, right? The perfect world, where every boy was only dating one girl, and every girl was only dating one boy at every particular moment in time. Yes? If only we lived in that world, right? Yeah? Sometimes the boys like to have more than one girlfriend, right? And that's still a function, it's still okay. But
It's like, is he arguing against
But that
polygamy?
particular,
Like,
but that particular function would not have a what? An inverse, right? Because not every x only has one y. Understand? Not every y only has one x. Good?
basically saying you cheat on Mr. Science on team.
Yeah, guys can cheat on girls, and it's still okay, right? Like this, the y is the guy and the x is the girl, right? So pretend this is the y value, right? So this is one guy because it's one y value, but he has how many girlfriends? 2 different girlfriends, right? I'm just gonna say one of them's positive, one of them's negative. I don't know. This is the x. Yes? Do I understand? Is it still a function? Does it pass the vertical line test?
Yes.
Yes. But which one does it fail? The horizontal line test. Because this is one y, but it has how many different x's? 2. Okay, so to fix that, what they do is they limit the domain. So they say, okay, we're going to have a parabola function, but we're not going to have the whole parabola, we're only going to have half of it. Or we only want the part of the parabola from here to here,